Which one is this? Let's go here. Okay. So I'm doing graphs and Subhan is doing trees. Uh, so I will be going over the first graph problem on the NeetCode website, NeetCode 150, and that is number of islands. We are given a m by n 2D binary grid called grid, which represents a map of ones, land, and zeros, which is water. And we want to return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume that all four edges of the grid are all surrounded by water. So uh basically what it's saying is if you want to count the number of islands, it's not as simple as counting the number of ones. What you have to do is check if the ones are adjacent to each other, and if they are, they're all considered one island. So that's why over here, all of these ones, since they're all connected together, either vertically or horizontally, diagonally does not count. It's all one island. Whereas with this one, you have one group of four ones in the corner. This is one island. Then you have one over here that is not vertically or horizontally connected to any other one. So this is its own island. And then you have two ones over here that is their own island. And for constraints, it is either 0 or 1. It's actually a list of strings here. It's a matrix of strings. There's a similar problem, which if we have time to go over, that'll be a matrix of integers. I don't know why they have strings for this one, but they do. So there are two methods we can go over. If we have time, I'll go over both of them. And one of them is breadth first search or BFS. The other is depth first search or DFS. I could briefly go over. Actually, I'll start with BFS and we'll briefly go over the approach of it. So BFS, the idea is that we will have some helper function called DFS. And what we're going to do is we are going to go through the grid, so each row and each column of the grid. And what we're going to check is if something is a 1 and if it has we have not visited it before, because in BFS you have the potential of like in any graph search, you always have to account for when you come to a node, have you seen it before or have you not seen it before? So if we encounter a new one that we have not seen before, then we can basically increase the island count. And then what we're also going to do is we can't just increase the island count. We have to go and check for any other ones that are attached to the same island. And then we also have to count them as visited. And the idea is we will have I guess I should start coding some of it. So the way we keep track of visitation is going to be a hash set, because in a hash set, you cannot have duplicates. You can check if some index is in a hash set, and that'll tell you if that is visited or not. So that's what we will start with. And then if we have time, we'll go over BFS. But we'll start with island count. This is going to be our final result. And then we also want to have a visited. This is going to be a hash set. So we will define it as such. And then what else do we need? We need a helper function. So we're going to call this BFS. I think there are other variables I need. I just can't remember them right now. And then BFS is going to go through and mark everything as visited, and then we will have some logic afterwards to dictate what do we do with how do we actually update the island count. I believe we also need the dimensions. So the dimensions of the grid, we can get it as follows. So to get the number of rows and the number of columns, we will use the length function. So I'm defining two variables simultaneously. Number of rows is going to be the length of the grid itself, because the grid is a list of lists. So since it's similar dimensions, like each list has the same length. So we can just we can get the number of lists. This will give us the number of rows. So that is length of grid. And then for number of columns, we can just look at how many elements in any one of these lists. So we can do length of grid 0 to get the number of elements in the first list. And then there is one more variable we need. We will define it in our BFS function. And BFS is doing breadth first search on a specific index, where RC is some row and some column. So when we perform BFS on some index, we will also need a list of directions. And directions is a two-dimensional array that tells us what directions we can go from a specific node. And because we only care about horizontal or vertical connections, we don't care about diagonal connections. That means we have to define those 4 directions up, down, left, or right inside this list. So we will have a list of possible directions. And we will basically use these to calculate new indices that we can go to. So one direction is up. One direction is left, or that's right. One direction is left. And then one direction is down. So we are just using 0 and 1 to represent up, down, left, right. And we won't define BFS yet. We will leave this for now and get back to it later. First, we are going to do the rest of the logic. So what we want to do is we want to go through every element in this grid. So that means we need a double for loop. So we're going to go through all the rows and all the columns.
Wait, sorry, what does a 0, 1, 1, 0, negative 1, 0 do?
They define the directions up, down, because like the index of a grid is represented by a list of lists. So like grid 3, 4 is like row 3, column 4. And then if we add these, if we add this set of numbers to this, we will get grid like 3, 5. So that'll tell us like this is the node to the right of this one. And then we also have a way to get to the up node, down node, left and right node.
Okay.
So that's what we're using those directions for. Because for breadth first search, you have to go to a node and then you have to check all of its neighbors. So like when you go to 1, you have to check its right neighbor, its bottom neighbor. We don't really care about this one. So that like we don't do -1, -1 to represent diagonal direction because we're not checking for that. But that's what these directions are for. We will be using them later when we define BFS, and then it might be more clear. But right now, what I said before is the way we define if something is an island, we have to use the visited because we need to keep track of what nodes we have visited and what nodes we have not. So what we're going to do is go through every index and then we're going to check. There are 2 conditions for something to be an island. Number 1, at the value at this index has to be 1. It cannot be 0. And then also our hash set is going to have a tuple which is a row index and a column index. So we will keep track of like both of these indices in our hash set. So if the pair that we are looking at, which is RC, is like I comma J, you can also think of that. If the pair of indices we are looking at is not invisited, that means we have found an island. So what are we going to do from here? We're going to call BFS on it because we need to basically visit all the neighbors, I guess is one way to explain it. So, and then we can also update our island count, which is what we will return at the end. And then that's really it for this. So at the end of this, we can just return island count because at this point, we will have gone through the entire grid. So unfortunately, we still need to define BFS. We're not done. So in BFS, we need to go and check all the neighbors and visit them accordingly. So commonly BFS uses a queue data structure. And for a queue, let me define it first, and then I'll talk about like some special things about it. In the one way to, there are several ways to define a queue in Python, but this is one way to do it, and it's better than the list implementation because I believe popping is faster. It's O of 1, as opposed to if you use a list, it's going to be O of n, I think. Although I'm not sure about that. But this should be one of the faster implementations. So here we are defining a queue. And a queue follows this principle, FIFO, which is first in, first out. We've covered stacks already, so stacks was last in, first out. Queue is first in, first out. What that means is that when you pop from a queue, you will pop like, if our queue is 1, 2, 3, and if we pop from this queue, we will get 1, or that will return 1. Whereas if this 1, 2, 3 was a stack and we pop from the stack, we would get 3 because that's the last thing in. So that's the difference between last in, first out and first in, first out. So for a queue, we will always be getting from the left. And the reason we need this data structure is because we need to keep track of what are the next nodes we need to go to for our search. In depth first search, for this problem, if you did it with depth first search, you actually don't need a data structure like this. Because with depth first search, you can just keep going in a certain direction. But over here, I mean, we can talk more when we get to DFS if we have time. But we do need this queue, and this queue is gonna contain, just like the visited contains a tuple of indices, this queue will also contain tuples of indices. So when we call BFS, we will only call BFS when we have found an island. So the first thing we need to do when we enter BFS is add our nodes, add this node to visited. So the way we do that is visited.add, and we will add this tuple r comma c to represent this index. We have now visited it. And we are also gonna add it to the queue. So we can do that by queue.append. This. I guess we can also call this queue, if that might make it easier. So we are adding to both our visited and our queue. And now what we're gonna do is we are gonna run BFS until the queue is empty. So while queue, what we are going to do is we are now going to, first thing we're going to do is pop from the queue. So we are going to get the front of whatever is at the queue. That is the first node that we have added. So to get that, we are going to do current R, comma, current C, which is like current indices is going to be equal to q dot pop left. And pop left is basically our way of popping from the front of the queue as opposed to popping the last element in the queue. So now that we have some node represented by these indices, we need to define all of its neighbors. And that's where we're going to use this directions list of lists. So the way to define all of its neighbors is we can use, we can structure a for loop like this. For increment R, comma, increment C in directions. And basically that's what's going to get us is like increment R could be 0, 1, -1, 0. And then increment C could be all of the right side of the tuples. So we are getting our directions. And when I say INCR, it means increment. So and the reason I'm calling it increment is because we are going to define our new pair of nodes, or like a neighbor node. And we will do that as follows. So we have our next R and our next C. They're going to be defined by this current R and current C plus the increment. So they're defined like this. And current C plus increment C. So what I'm saying is I'm getting the next pair of nodes. This could be either the up node, down node, left node, or right node. We're going to go through all of them from a specific node. But now we have this new pair of indices. What are we going to do with it? We're going to determine if it's part of the same island. So if, and there's going to be a really big set of conditions here. But if we meet a certain set of conditions, what we're gonna do is just like we added RNC to our visited and to our queue, we're gonna add this new RNC to our visited and our queue, if a certain set of conditions are met. But let's add them first. So just like this, we're gonna do the same logic here. But instead of adding R and C, we are doing next R and next C. So next R and then next C. What I'm saying is we're gonna add like the neighbor node to our visited and our queue. How do we know when to do this? Well, first of all, we need to check, since we can go up, down, left, or right, we need to check if we're still within the grid. Because if you're at this position and if you go up, you're no longer in the grid anymore. So first we need to check if next R is in range of num rows. And same for columns. So next C is in range num columns.
What
So
does range
that,
do? Is that like a Python like?
yeah, so range, this should basically give you like, otherwise I think you would have to predefine what the range is and put some inequality. But range should tell you like, because num rows is going to be some number from 0 to whatever. And here it's going to be 0, 1, 2, 3, 4, 5, 0 to 5. If our index is not in the range of 0 to 5, then we don't want to do this stuff. So that is just making sure we haven't escaped the grid. There are two more conditions we also need. We need to check, just like down here, we need these two conditions. So we need to check if grid of next R, next C, if at this position we have a 1. Because if we don't, it cannot be an island or part of this island. And then we also need to check if next R, comma, next C is not visited. So what are these four conditions again? So we found some neighboring node. It's either up, down, left, or right of our previous node. And we are checking if this new node is in the range of the grid. If it's a 1, and if we have not visited yet, then we can add it to our visited, we can add it to our queue, and then we also need to run BFS on that new node. So that is what this if condition takes care of. And I think that should be our BFS. Because basically the goal of BFS, I guess I should do this. BFS takes care of visitations.
Yeah, so I think that's important here. The thing which you are doing for visited, because otherwise, if you don't check this condition, then you are visiting lots of nodes, because you're when you are on the first node, you are checking left, right, top, and bottom. When your second node, you're still doing left, right, whereas you already processed the left node.
Yeah.
So I think this visited thing is probably important to make sure that you don't unnecessarily evaluate these conditions again and again.
Yeah. And especially here, it's important because if you don't, then you could go back to a 1 that you already had, and then you would still increase the island count. And then you would have way more islands than you're supposed to have. So that
Hey,
is
before you go too far, I was gonna ask. So this is BFS. Is this for a grid or is this for a tree? Because or you are or the grid is implemented as a tree. So can you?
This is implemented as a graph.
it should be implemented as a graph because in
Oh,
the
it is
top of
implemented as
this,
a graph. Okay.
yeah, it's implemented as a graph. To be honest, I'm not there is another problem where like this seems to me like an unconnected graph, and that's why we need to do this for range. Like we have to go through the entire grid, because if we don't go through the entire grid in BFS, people who take data structures will know, in BFS, if you just do BFS on one node, you may not reach every node in the graph,
I
which
see.
is why we have to go through the entire grid. And for this specific problem, we have to go through the entire grid anyway, because you have ones and zeros. Zeros represent disconnections, but you have to find all the islands within that grid. So the video solution did not recommend a faster solution than this,
Okay.
which means like this is like a fairly fast way to do it. And the time complexity for this is It's going to be O of M times N times some constant. And I'll explain this. So M is the number of rows, N is the number of columns. We are going through all of the rows and the columns. And then the constant, we're doing BFS repeatedly, and BFS has some constant runtime. Because the queue is not going to be, like, the queue is going to have some
Q
constant.
is small. Q is small, but yeah. So here also in the second if for loop also you're not going through everything because there is an if condition in there which is not letting you go through all the nodes.
Yeah.
Which is good. What did I forget? Yeah, one other thing I was going to ask that it's a string. Nodes are all strings. But is this
Yes.
arithmetic works fine with the like the plus minus direction stuff works fine with the
Yep. Because the directions are, like, the indices are still integers, but the values are strings. So the indices, like if I add 1 to some index,
Got it. Yeah.
that'll work.
Yeah. Okay.
There is a different problem where the value is an integer, and all you have to do is change this 1 to an integer 1. That's it.
Okay. Okay. Yeah. No, this is fine.
That's it for the BFS implementation of this problem. I don't know. We can go over the DFS implementation, or maybe Subhan can do a problem, and then if we have time, we can come back to this.
I can do like a BFS tree problem.
Sure.
Okay.
Yeah, this is some serious stuff, guys. I mean, we were doing simpler stuff. Good job, Taha, on that.
Thank you. Actually, I was a bit surprised on how hard it was, because I think Subhan could agree with me on this. In our data structures courses, the graphs are usually the easy part out of everything, but actually in those classes, we didn't actually code the graphs, at least with my professors. It was mainly pseudocode. So, or like doing the problem on paper, like with a diagram and stuff. So that is very different from coding it. Hopefully it gets easier.
All right, what are you doing next? Subhan, are you doing something?
Yeah, let me share my screen. Give me a second. So yeah, this is question called even odd tree. So it says that a binary tree is named even odd if it meets the following conditions. The root of the binary tree if it's at level index 0. So it's just saying that like this is level 0, this is level 1, this is level 2, this is level 3. And it says for every even index level, all nodes at the level have odd integers values in strictly increasing order. So for the even ones are like 3, 7, 9, right? Since this is level 2 and 2 is even. Level 0 is even, so there's just one number here which works. So you see here they're also strictly increasing with 3, 7, and 9. For every odd level, there are even numbers and they're in decreasing order. So for level 1, which is odd, you see 10 and it goes to 4, and then 12, 8, 6, and 2. So the way to solve this is we're going to use a breadth first search or BFS approach. And what we're going to do is we're going to search through each level. So BFS is essentially we go level like, so a depth first search, which just means we all go all the way down until we can't reach like the left or right subtree, right? But breadth first search is like kind of the other way where we look like level through level from the nodes.
No, so Subhan, one thing I'm gonna add here, I was gonna ask Abdullah on that also, Taha. But since this is a tree, so when we were studying the trees, they were like 3 kind of traversal: in order, pre-order, post-order. So you guys also understand how they are related to breadth first and depth first, right? In order, pre-order.
I did learn that. I would have to review the differences.
I
think they are related. I think my understanding is that in order is depth first.
That was not what I recalled. From what I remember is it's like you can do any of them in BFS. Subhan, is that right? Like
What-
I feel like when I studied them, they seemed unrelated to
Oh,
me,
they're unrelated?
or at least not directly related.
Because I remember
No, I don't think so. They are related. It's just if you see the traversal order, let's say if you're doing for in order, then you would go to the left node and basically, you know, to the last left, the node,
Yeah.
and then the route comes the last one to traverse, right? So in this case, like 1, 10, 3, 12, 18. So in this case, the LLR, let's say if R is the root and right node is R, then you will see LRN is going to be the in order
Okay,
in that case.
okay.
So the output will be 12, 8, 3, right? And then you move forward, right? So in this case,
That's in order, right? That's in order.
in order, yeah.
Okay, okay.
Also, one more thing is, let's say if you are trying, somebody is giving you a sequence and they want to really flip the order, you can do an in-order search. Sorry, the in-order search, and the output will be actually the reversed output of the tree. So there are some quick tricks to that, but just to say, I mean, in my opinion, I don't think that they were related to
They're
BFS,
not
but
related. Okay.
yeah.
Sounds good. Okay, Subhan. Yeah, sorry. Keep going.
Yeah, so we're gonna have to do a breadth first search here, which means we search through each level, and at each level, we're first gonna check if that level number is a even or odd number. Then, if we check if it's an odd number, what we're gonna do is we're gonna check if the level is odd, we're gonna check are the nodes in that level, are they even? If they're even, the next thing we check for is if they're strictly decreasing. So let's first do the first step where we have to check let's do our first breadth first search. So to do breadth first search, we're gonna create a queue. So by doing that, I'll just create a dequeue, which is in Python, and I'm just gonna append the root to it. We'll do the base case, which is basically if root is none, we're just gonna return. So we're just gonna add the root to our queue. You're gonna use a queue approach because in BFS we want to use the first in first out for checking our nodes. So we're gonna do is we're gonna do while queue, and now inside of here, right, inside of our while loop, while we there is a like a node in the queue, right, we're gonna add our level, right? We're gonna say we're at a new level. And to start this off, I'm gonna set a level here outside of the BFS equal to -1. I'm doing this so that when the first time I go through this thing, -1 plus 1 will be equal 0, and that will be the first level of the tree, since over here it starts at 0. So all we're doing here is incrementing level by 1. We're going to then loop through the queue, right? So we're gonna loop through the current queue that we're at. So I could just create a variable here called size, then queue, and just put our size in here. So we're gonna loop through whatever is in our current queue. What's currently gonna be in our queue is just a node 1. So for the value 1, what are we gonna check? We're first gonna check if the level is an odd or even number. So we're gonna do if level %2 is equal to 0. This means this is an even level, right? Because if we do a mod by 2, and for example, 0 mod 2 is 0, 4 mod 2 is 0, 6 mod 2 is 0, right? That means that it's even. And then we're gonna have our else, which is gonna be the odd level. But we're first gonna work on the even level ones. So over here, what we're gonna check is we're gonna check at the current level if the node So we have to get the node out first, right? So to get the node out first, what we're gonna do here is we're gonna pop it from our queue. We're gonna pop the 1 from our queue. So we're gonna set a variable named pop, which will be equal to q dot pop left. We're doing pop left because when you want to pop from a queue, we have this value that just pops it from the most leftmost value, which is essentially the first in or first out, because our queue is currently at this. If it was like 1, 2, and we want to pop out of a queue, we always need to do a pop left, since that gives us the first number. So we're gonna pop out of the queue, and then what we're gonna do is check at the even level, right? If pop dot val, since we're getting the value, if that is what do we have to check? We have to check if the pop value, right, which is here is 1. We have to check if it's an odd number, right? So what I'm gonna do here is I'm gonna say if it's an even number. So I'm gonna do here is I'm gonna say if pop mod 2 is equal to 1. What does this mean? This means that if this is an odd number, right? So instead of checking if it's an odd number, I'm gonna check if it's an even number. So I'm gonna say if pop.val mod 2 is not equal to 1. This is basically saying the same thing if pop.val is an even number, right? And if it's an even number, we want to return false. So I can do the same thing as just doing pop.val %2 is equal to 0. That's better. What I'm gonna do here is just return false. That means that this was an even number and we can't have even numbers over here. Then we have to check another thing. We have to check if now we have to check if they are increasing, right? Because you see in the even number values, it's like 3, 7, and 9, right? So how can we check if a number is increasing? What we can do is we can check the previous value. How do we get the previous value? We can create a variable here before we loop through the queue, such as we can call it previous, and we can just set it equal to none for right now. So we have a value called prev, and what we want to do is basically after we check the even and odd level of our after we check the levels, right, we want to set previous equal to the current value. So what I'm going to do here is do previous is equal to pop.value. And for example, we're checking 1 here right now, right? And since 1 is the only number here, we don't need to check a previous number, right? So what I can do here is I can say if previous is not none. This means that what I'm trying to say here is that if the previous is none, that means we're just gonna skip through this if statement or this conditional over here, because there's no previous number here, which means that no matter what value is here, it will work, right? Since there's no previous value. So if previous is not none, so imagine we're looking at this level over here, level 2, and say we're checking the node 7. What we're gonna do here is we're gonna say our previous value will be 3. So what do we need to check? We need to see if the previous value, which is 3, it needs to be greater than 7 for it to return false, right? So I'm gonna say if previous is not none and prev is greater than or equal to pop.val, right? Because say this value prev was greater than this current value, which is the current value we have popped in our breadth first search. This means that this should return false as well, right? So after, for example, after we search to the 7, so then after we do all this checking, we're just gonna set the current value to prev. So in our next search, when we're searching a 9 value, we then know that the prev value was 7, and then we do the same thing for 9. So that is for the odd value, or this is for the even level, sorry. Yeah, this is for the even level. Now let's do it for the odd level. For the odd level, it's the similar thing. We're gonna say if pop.val percent mod 2 is, so let's see. We want to check the odd values, the odd levels, right? So the odd levels are when it's like level 1, and it's when they're even. So I'm gonna say if it's not equal to 0. This means that if these are odd numbers, we want to return false. Because we want even numbers in the odd levels. And then what we're gonna check is the same thing. If prev is not none and prev, but this time, since they're decreasing, what we want to do is say if the previous value, for example, if our current node that we're checking is 8, we want to say if the previous value is less than the current value, then we want to return false. So we're gonna say less than or equal to pop.val. Then we're just gonna return false. So now what we have done here is we've checked the even levels. We've checked if they have we've checked if the current value is a even or odd number, and we've checked if their previous are either increasing or decreasing based off of if it's an even level or an odd level. So now we have to do one more thing here is we need to add the left and right children of the current node to the queue, right? Because after we're done with this level, we need to check the children of the node, for example, the left and right. To do that, it's pretty easy. All we're gonna do is say if pop.left, if there is a pop.left that exists, we're just gonna add it to the queue. And if there's a pop.right, we're gonna add that to the queue as well. So after doing all of this, for example, we'll be done with this first level over here. Then since our current level is 0, we go back to the queue and we increment level. So now it will be a level 1 now. And at level 1, we will know that 1 mod 2, which is equal to 1, right? So we should be looking at the odd levels, right? And at the odd levels, we'll check 10 first. 10 mod 2, that is equal to 0, right? Or
Yeah.
yeah, it's not, it is equal to 0, right? So it won't go to this. And since in the beginning the prev is always set to null when we're checking a new level, since it's the first value, we should not even go to this, right? But at the 4, since our prev will be 10, we can then check is 10 less than or equal to 4. It's not, so then we won't return false. And then we add the children to the queue, which are when we're searching through node 10, it will be just 3, and at node 4 it will be 7 and 9. So after doing all of this, we can then say that since we're able to search through the whole each level through a BFS, we know that we weren't able to return a false value, which means that we should return a true over here. And that should be the solution, I think. Yeah. So this stumped me pretty hard the first time I did it, but it makes a lot of sense once you get the pattern, which is that there are many questions in LeetCode that just say that like check something through every time there's a new level in the tree. So all you have to do is like at each level do the breadth first search, check whatever things you need to check, for example if it's an even index or if it's an odd index, and then add the children to the queue and then go to the next level.
So the problem that is asked in a interview is that they specifically ask that this is a tree and you parse it, and it's a binary tree, you parse the tree and look at certain thing on the certain level, or they will give you more word kind of a problem, which might not tell that this is a tree.
No,
Uh,
usually they'll say like we have a binary tree. If it's a binary tree question, it's usually they'll indicate that's a tree, or if it's a graph, they'll indicate that it's like a graph.
Yeah.
Because here you have to know it's a
Because
tree.
they are not asking you to populate it, they're asking you to check
Do a
something.
check. Yeah.
Okay, so if they give you a problem where you have to think about which data structure to use yourself, then the problem would not necessarily be about do something in a certain level, right?
I
Uh,
think so. They will tell you it's a tree because they have to in this type of question. But what they might not indicate is if you want to do it in a depth first search or a breadth first search.
Oh,
So the reason why I use a breadth first search approach to this problem was because every time it indicates that we need to check through every level, right? Here it's an easy like giveaway where it says level 0, level 1, level 2, level 3. If we were to a depth first search, it doesn't make any sense because we will be going down this like children like this tree right here, right? And these are all at different levels, right? So there's no point of checking it through that way. The best way is to do like check through it through a breadth first search way. We're just checking each level.
yeah, I think the problems where they will not tell you maybe is that you have populated the data in some kind of a tree and then you have to search it. That's when maybe they will not tell you if it's a tree or not. I don't know. Asim bhai, what's your opinion on that?
What's the questions? Can you repeat that again?
So like in this case, they already know that this is a tree, right? And they have to go breadth first search or depth first search. Is that normal that they will ask a question like this, or they will give them some other more problem where it's more descriptive of a problem, and then the kids have to decide, or these guys have to decide which approach to take?
I mean, for entry level type of roles, they won't make it very ambiguous. You see
I
what I'm
see.
saying? But like if you're going for some high level, they will not be very descriptive. Like there is a binary, there's a binary tree or something.
I see.
But they won't make it like that. They would just be very generic to and let you use the type of data structure that you feel that is going to solve that problem, right?
Mhm.
Sometimes you have to model the problem
Yeah.
to a data structure. I have seen that type of interviews, like that's for level 6, level 7, that type of interviews.
Yeah.
But where you will be given, or maybe just to optimize it, the current problem to, So I have a question on this one, if I may ask.
Sure.
So I see you are, and I'm just following it because I've not done BFS I've not done the tree problems for some time. So how are you? I know that when you get into this queue and then you are increasing the level. So how do you really know that you have processed everything in that level? How do you know that?
Yeah, so it's in this for loop, right? So for example, in the beginning of the code, we append the root, right? Since we're gonna append the first node in the tree. By doing that, what we're saying is that then we do a while loop, which just says while there is always something in the queue.
Right.
Because always gonna be something in the queue, right? Until we enter the bottom of here, because we're always adding something to the queue inside of our for loop. We're always adding the children. So then inside of the current size of the queue, which is just 1, right? We're just gonna loop through this one time, right? Since there's only one node. And what we're gonna do here is we're gonna pop this node and do all of the even odd checking. And then we're going to add the children, which are 10 and 4 to the queue. So now when we go through the So then when we go through the so we're gonna return back to over here to the code when we're done adding the children. Then what we're gonna do here is we're gonna increment level, and then we're gonna get the next size. The next size will be 2, right? Because we've added 10 and 4, which are the children of 1. So we're gonna check 10 first, since 10 is the first value in our queue, because it's always first in, first out, and I'm adding the left node first, right? By doing pop.left first. So then we check 10. We're going to do all the checking for the even and odd, and then we're gonna add the left and right nodes of 10. It doesn't have a right node, so we're gonna skip that, but it's gonna add the 4, or it's gonna add the 3, sorry. So then it has now 3. So the current queue after that will be 4 and 3, right? Because we haven't processed 4. Then we're gonna pop
How
4.
did you how did you land to 4 then? You
Because
did a q dot left, you got 10, right? Then you did q dot right, and then okay, so you got that 4 is in the queue now, right?
yeah. So it was 10 and 4, right? In the beginning.
Right.
We did a pop left of 10 because it's a queue. We checked 10's 10's children, which is just 3. Then what we do here is we're still in that current for loop, which is just the size of the previous children, which was 10 and 4. So we still have to process 4. We process 4 by doing the even odd stuff. We pop it. We add 4's children, which are 7 and 9. So
See,
then our
I-
queue will now consist of this, which is the 3rd level.
let's take a step back. So when you added the root node, right? When you
Yeah.
added the root node, okay, so you said, okay, I'm just going to add the root node, and then what you said, as soon as you see, you started processing. You said, okay, let me check the moment you added the root node in the before you entered the queue, you actually had root node added, right? So the level was
Over here.
yeah. So so there was something in the queue, so you started processing. And then you looked into all those things, you processed that single node, right? And then, so I think the code when it starts with assumes, okay, let me see, let me just process everything that's in the queue, and then I'm going to see my left and right, basically.
Yeah. So we're just gonna process just the current node in the queue, or the current node that we popped from the queue. So in this case, it's 1. For 1, we do all this checking, and then the main part of the breadth first search is just checking, appending the left and appending the right. So then we would then append, it would just be 10 and 4.
And
Right.
then,
We popped 1 already, which is over here.
oh, you already popped it out, so the 1 is gone now because it didn't.
What I could do is just I could like move this code. Like this is basically the simple breadth first search, and all this stuff over here is like the actual part of the question.
Yeah. So then, yeah, okay. I was so the each object that you are taking is a tree, is a node object, right? Node object in
Yeah.
the queue.
Yeah, it's a tree node. So it has a value, a left and a right pointer.
Okay. Right, very good, man.
Yep. Exactly.
Okay, are you guys doing more? Okay, you guys are done for today.
Up to you. I think we can't
It's
do a
going to
new
be Maghrib
problem.
time soon, Taha. Yeah, I'm sorry to interrupt you guys. We're gonna have to go for Maghrib like in 5 minutes.
Okay, no problem. Yeah, we can continue next time, inshallah.
Yeah, let's do
Are
others.
you guys looking for a full-time roles, or what are you looking?
I'm looking for internships for next summer, inshallah, but then after that, I will be looking for full-time roles.
Okay, you can send me your resumes,
Okay,
and I can forward it to a few hiring managers.
oh, Jazakallah khair. Thank you so much. That would be a
I
great help.
just want you just to make sure that you I mean, I'll give some feedback, but just make sure if you're good with Python, right? Basically, just make sure you have a proficiency, express your skills with the language, and also if you're going for sort of an internship type of thing, like you just mentioned, like the type of courses you have taken.
Yeah.
In the first shot, and also project, right? Basically.
you know
Yeah.
if Palo Alto they've opened up their any new grad positions?
We used to work for Palo Alto, so I know a lot of hiring managers there. So I can forward it to one of the hiring managers. It's just that you just need to make. I'll talk about the format of the resume, right?
Okay.
But like just make sure that you have your tech stack and everything,
Yeah.
very well outlined in the resume.
Sure. Jazakallah khair. Thank you so much. Should we just send it to you privately?
Let's do one thing. When you have time, I can sit with you for 10-15 minutes and tell you the format of the resume. And
Sure.
then you can ping me. I'm sorry, I was very busy during the week, but I can work with you. There are a few people. There's one role in Apple Pay. I know the hiring manager there, and also in Palo Alto. So most likely, I'll ask for the interview for you for sure. Right? Basically.
Jazakallah khair. Thank you so much. So we can
Okay.
send you on WhatsApp and then coordinate a meeting.
Let's send me on the email. I'll give it my email to. You can post in the WhatsApp, or Naeem Bhai has my email too, so I'll just post it there.
Yeah,
Okay.
either way, you guys can forward me your resume. I think Subhan's resume. I think I thought I sent you Asim bhai. Okay, nahi abhi tak.
Yeah. Also, make sure if have some security type of mention if you're going both the if you have like a some DevOps type of skills also, right? Talk about those, right?
Okay. I don't have any of those, but I'll see if there's anything else I can think of.
I'll talk to you about. Let's discuss resume later, inshallah.
Sure. Jazakallah khair.
We did some DevOps stuff in our previous project, Taha, but we can talk about it maybe one of
It
the.
doesn't need to be very serious, honestly speaking, but you should know like basics about branching, rollout,
Yeah, Git stuff you guys need to get familiar. I think Subhan, you and Taha, both of you, I think are
I
familiar.
will dive you through. I will take a session. I'll give you everything on DevOps thing. That
Perfect,
should be
perfect.
inshallah.
So why don't you guys set up a meeting with Asim bhai and then maybe you guys.
I will tell you basics of when you're going into interview, and I will tell you, okay, how did you run the project and how did you do it? So once you take that script and you talk on those, and you should be good.
Okay. Jazakallah khair.
Okay. Assalamu alaikum.
Wa alaikum assalam wa rahmatullahi wa barakatuh.